All right, this is where we're headed here in this chapter. It's explaining why things are true. And when it says explain, it doesn't necessarily mean words. We're going to explain by showing, using math ideas, that one side is equal to the other side. Sine of theta, cosecant of theta is going to be equal to tangent of theta, cotangent of theta, all of the time. That is always a true statement. It is never not true if you plug in the same thing for theta. Okay? Why? Anybody have an idea why that's true? Lucas, what you got? These two things are reciprocals of each other. Sine and cosecant. Those are reciprocals. And if you take two reciprocals and you multiply them together, it's going to get you 1 every single time. Okay? That is the perfect idea of what's going on here. I don't suggest that you ever use x, y, and r after the intro, but let's use it right now. So let's use x, y, and r. What is sine in terms of x, y, and r? Sine is y over r. Cosecant is r over y. We're multiplying. It's one big old fraction bar. We could cancel. R times r, that's going to cancel. Y times y, that's going to cancel. When things cancel, when you multiply, what is that going to leave me with? 1. That's important to make sure you understand that. Tangent and cotangent. Well, tangent, that's y over x. Cotangent, that's x over y. It's multiplied, one giant fraction bar. Cancel, cancel, 1. Is 1 equal to 1? Yes, then we're good. That's the whole goal. To show that they're equal, all I got to do is get the same thing on both sides. And just using simple math ideas, we are able to do that. And if we get them both equal to each side, then we've proven our idea. Remember learning proofs back in geometry? Remember doing that? You talked about like postulates and theorems and all that stuff. These are proofs, but they're way different. They're not the same thing. You don't have to remember postulates and theorems. You got to remember stuff like that that'll make one side equal to the other. Let's go to the next one. Cotangent of x equals cosine of x over sine of x. Same idea. This is an important one. This is something you should know. When you think cotangent, cotangent is cosine over sine. But let's show why that's true. What does cotangent mean? X over y. And then I've got cosine, which is x over r. And I'm dividing that by sine, which is y over r. I'm taking two things and I am dividing fractions. I don't want to divide fractions. This right here looks super ugly. If I'm dividing fractions, that is the same thing as what? Multiplying by the reciprocal. So dividing this fraction, great. I'm going to multiply by the reciprocal. I'm going to multiply by r over y. One giant fraction bar. Cancel the r's. X over y equals x over y. Yeah, that's a true statement. Okay? When we get to this point at the end, we need to show that, hey, I was trying to show that they were equal to each other, and they are equal to each other. We're going to put an ending mark. Okay, there's a couple different options. That's the one right here. This is what my college professor always did, so that's what I do. Okay, it's called an ending mark, basically showing, hey, I was trying to show that they're equal, and now they are actually equal to each other. Okay, I call that the end of the road. It's kind of a line with a line at the end. It feels really satisfying when you're done to make that mark. But there's other ones. That's not the only one. I got very, here, let's just type it in. End of proof. Type in end of proof. We'll go to Wikipedia. Boom, there it is. Oh, this is different than the one I got last time. They see I'm getting all different ones. Here's this one. On the top here, this is, yeah, there we go, tombstone. Okay, that's the one I meant to click on. Tombstone. In mathematics, the tombstone is a symbol used to decide the end of a proof. So this is a tombstone right here. A square or a rectangle or this guy or that guy or that guy. Those are all called a tombstone. You put it at the end of a math problem when you've proved it, basically showing, hey, I killed that problem. Okay, I dominated. I win. I put that at the end to show that I'm done with my argument. You could also do the end of the road, or if you want to be super cool, you could put QED at the end of your problem. QED represents the Latin phrase quod erat demonstratum. And that means which was to be demonstrated. Basically, I was trying to show this. QED, I showed what I was trying to show. My brother used to be a math teacher. He's now a principal, but he's a bigger nerd than me. And when we were growing up, we used to get in arguments. And when he wanted to finish his argument, he would say QED. Super nerdy. But It happens. All right. So with that being said, let's take a quiz. Yay! Let's take a quiz. We're going to practice and see how much you can think on your own. Get your brain warmed up again. Any of these in particular that you want me to go over? Hey, I'm looking at number 7 and I don't understand it. I would love to go over those. Earlier I went through about 4 or 5. Anyone in particular you want to see? So number 7, it's an easy one, but it's one that if you don't remember even odd identities, then you're just going to be stuck. And so when I look at number 7, I see secant, and I don't love secant, so let's write it as cosine instead. It would be this. If I'm doing cosine and I have a negative angle, what do we do with that negative angle when we're dealing with cosine? We ignore it. With cosine and it's negative, we ignore that angle, and so that is the same as that right there. So 1 over cosine squared, it's really just positive, which means it's letter M because it's 1 over secant squared with a positive x. It's not the other one that's up there. Any other ones? Anything else you need to see? This is the baby steps. So if you're looking at this, and we all did well in here. I'm not worried because we did pretty well with that. It's going to get a lot harder than this really quickly. All right. So that's good or bad, probably bad, but we'll see it. Okay. Again, like I said, second semester goes a little bit slower. I added an extra day to what we're going to do pacing wise today. Like I was working through it and I was like, hey, we could slow down. Let's slow down and make sure we know it. But we're going to figure this out pretty quickly. Let's go to those notes I passed out. We're going to get into some pretty tricky problems by the time we get done. But everything in this chapter falls under the category of trigonometric identities. First of all, the word trigonometric is probably the best word in the English language. Go ahead and say it for me. It just rolls. It's got a good flow to it. It feels good when you say it. A trigonometric identity is just a fancy way of saying a trig statement. It's a trig statement that is always true. No matter what your theta is, it's always going to be a true answer. Okay, no matter what the angle is. I could plug in any angle. So like the 2 bell work questions, we could have plugged in any number for theta and it would have worked. Okay, we already know some trigonometric identities. We know even in odd identities. You might have forgotten them, but we know these things. We know that if you have a negative angle with sine, that you can just bring the negative out in front. If it's cosine, we just ignore the negative. If it's tangent, we bring the negative in front. We've done those. These, we haven't done as much, but they should make sense to you as well. Trigonometric functions. Okay, cosecant, oh yeah, that's 1 over sine. That one's easy. And secant is 1 over cosine. This one right here, we have not talked about a lot. We've talked about it a couple times, but it's really necessary. Tangent is sine over cosine. Okay, think about what tangent means. Tangent is y over x, and sine means y, and cosine means x. Tangent is the same thing as sine over cosine, and vice versa. Cotangent is cosine over sine. Those are things you need to know. And then the last set of things you need to know are Pythagorean identities. We've dealt with those a lot. We just did them in that warm-up, but we're going to continue using Pythagorean identities. Everybody good with that? So our job is to solve these identities, okay? Whether we're proving that they're true or we're simplifying, we're going to do both. And today what we're going to talk about are 4 major skills that we're going to use to help us solve them, okay? These problems can be really tough. There are some that I look at and I get stuck and I have to spend 5-10 minutes working on a single problem. That's a long time, okay? Because they're complex, but these are puzzles. You're going to try to look at them and figure out a way to make the pieces fit with each other and be able to solve them, okay? And what I'm teaching you today are skills that are going to help you to solve these problems as we work. So today we're going to do 4 different skills. We're going to talk about each one individually. First thing we're going to do is learn how to simplify by just writing stuff in terms of sine and cosine. This is going to probably be the most used skill. If you can rewrite stuff in terms of sine and cosine, you probably should. Okay, not all the time, but that's a good skill to have. So there are 2 different problems we're going to do today. We're going to do problems like this, which are just a simplified problem. And then we're going to do a problem like this, which is, oh man, I did this problem first period. Make that a 1. That's what I get for making a problem at lunch. Oh, no, that problem is completely bad. We're just not going to do B. I made these problems at lunch. That's a completely bad problem. All right. But this is a skill we're going to do all the time. Okay. Rewrite in terms of sine and cosine. Here we go. Let's do letter A. Cotangent of theta over cosecant of theta. Let's simplify that. So the first thing we're going to do is rewrite stuff in terms of sine and cosine. So when I see cotangent, I don't want to talk about cotangent. I want to write it in terms of sine and cosine. What could I replace cotangent with? It is cosine over sine, because cotangent means x over y. So x is cosine, y is sine. Boom, I got that. I am taking that and I'm dividing it by cosecant. That's 1 over sine. Okay, well, that's not simplified yet. We need to keep simplifying. I'm taking a fraction, I'm dividing by a fraction. What can I do if I'm dividing by a fraction? Multiply by the reciprocal. So instead of dividing by 1 over sine, I'm going to multiply by sine over 1. I am multiplying. Make a big old fraction bar because I'm just multiplying. What can I do to simplify now? Signs are gone. They got 1 on top, 1 on bottom. They can cancel. I am left with cosine theta. That is the simplified version of this problem. We went ahead and simplified that thing down. We kept simplifying until we got it by itself. Kind of makes sense so far. All right, let's look at this next one. Can I do this one? Let me look. Give me a half a second. All right, it's equal to 1, not 2, because I made a mistake. Now, this problem, we are showing that they're equal. They told you the answer. The last one, we didn't know what the answer was. It was cosine. This one, they already told you the answer. You're just trying to show the right answer. Okay, so let's work through this. Tangent of theta divided by cosine. What does tangent mean? Sine over cosine. Okay, sine over cosine. I'm dividing by cosine. Or in other words, I'm multiplying by 1 over cosine because it's being divided by that. If I'm dividing in it, I could multiply by the reciprocal, same idea. So far, I took this and made it that. Cool. Then I've got cosine squared and sine. That's already in terms of sine and cosine, so I don't really have to mess with that. And then I've got plus 1 over secant squared. The reciprocal of secant. What could I do with the reciprocal of secant? I want to write that in terms of sine and cosine. What could I do? Just make it cosine squared. I'm doing the reciprocal of a reciprocal. If I flip it twice, it's going to get back to what I want it to be, which is just cosine squared. And that's supposed to be all equal to 1. Everybody go with me to this point. Solve it the rest of the way. Go. Here we go. Sean, what'd you do? Yep. Good. I have cosine squared on bottom. He's got cosine times cosine. That's cosine squared. What do you have on top? He's got a cosine squared on top. Those two things, two of cosines are on top, 2 cosines on the bottom. They cancel. Okay, they all cancel out. So what are you left with there, Sean, when you multiply all that stuff together? Sine squared, because sine times sine, plus cosine squared equals 1. Is that a true statement? Yeah, because this right here is 1. Go ahead and write that last step where you're showing that both sides are the same. So like 1 equals 1. If we're proving it, now we've proved it, we got to put some sort of ending mark, whether you want to write QED or the end of the road. I'm going to throw a tombstone at the end to show that I win. Questions on that first one? On the second? Let's do it again. Okay, so first step, sine and cosine. That is the most used one. I would say the next most used one is multiplying by conjugates. And we'll show you why this is helpful. Okay, I haven't used this one enough in the past. You can solve problems in lots of different ways. Multiplying by conjugates normally make things a lot easier. Okay, remember what a conjugate is. A conjugate is this guy right here, where one of them is plus and one of them is minus. Okay, that's the thing we're looking at. So in this case, let's multiply these conjugates together. Okay, let's multiply them together. So I'm going to take secant times secant. What is secant times secant going to get me? Secant squared. And then I'm going to take secant times negative tangent. Ugh. Negative secant tangent is what I'm going to write. I'm just going to write it out. All right, then I'm going to do the other thing, multiplied both of them. So tangent times secant. So tangent times secant, I'm just going to put it in alphabetical order. Secant tangent. It's just two things being multiplied together. I don't know what they are. They're just random. Okay, and then the last thing I'm going to do is take tangent times negative tangent. Tangent times a negative tangent is going to get me negative tangent squared. What happens when I multiplied those conjugates together? This guy right here and that guy right there. I've got a negative secant tangent. I've got a positive secant tangent. When I add them together, what does that get me? 0. We say cancel it out a lot. There's a difference between this canceling out when we add them and when we multiply. But those two things cancel. So I'm left with secant squared x minus tangent squared x. If you see ones and squares, your brain should think, ooh, Pythagorean identities. Ones and squares, Pythagorean identities. Anything we can do with secant squared minus tangent squared? What is secant squared minus tangent squared going to get me? 1. The answer is 1 there. So by multiplying by a conjugate, it made it a lot simpler. Instead of that craziness that started, we got to the answer of 1. Conjugates help in a lot of different ways. Good on the first one. Let's try it again. This time, we're trying to prove that it's true. Cosine over 1 over sine, blah, 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 blah. So we look at this. I see a 1. I see a sine. My brain right now is already thinking, hey, I can make a conjugate here. Let's do that. What is the conjugate of 1 plus sine? 1 minus sine. And I can't just multiply something in this problem by 1 minus sine. That changes the problem. Okay? For example, if I have the number 3 over 1 and I just multiply it by 4, is that the same problem? If I randomly multiply, is it still 3? No, it changed. Now it's 12. But if I multiply by 4 on top and 4 on bottom, does that change the problem? No, because 4 over 4 is just 1. I didn't change anything. The same idea is going to be happening here. Hey, I want to multiply this by the conjugate, but this changes the problem. So instead, I'm going to multiply both the top and the bottom by the conjugate. You are never going to use this in your job. The things we're talking about with solving them, you're not going to use them. But what you will use is problem solving, trying different methods and figuring out what's working, and then also just fractions. This concept that you can multiply the top and bottom by the same thing and not change anything, yeah, that's a skill you need. Okay, that's what we're going to build more than anything else. All right, let's multiply. So I'm taking this times that. I'm going to do it over here to the side. This is one you should know, though, or you should get the hang of and get really good at. 1 minus sine times 1 plus sine. When you multiply conjugates like this, 1 times 1 is 1. 1 times sine is sine. Negative sine times 1 is negative sine. And negative sine times sine is negative sine squared. What happens when you multiply conjugates? Middle term cancels. That's important. On bottom, I've got 1 minus sine squared. On top, I'm just going to leave it for right now. I'm not going to FOIL it out. I'm just going to leave it. And you'll see why here in a second. And the whole goal is to make it equal to this side. I want to make it equal to that side over there. 1 minus sine all over cosine. Anything, have any clues to what we could do next as we look at this problem? We need to get rid of this cosine. Look at what it's supposed to look like. There's no cosine on top. This one has a cosine on top. I only need one cosine on bottom. Right now it says 1 minus sine squared. You look at this thing. You see a 1. You see a squared. What should your eyes or what should your brain think about? Boom, right here. What is 1 minus sine squared going to be equal to if I move this sine squared over? It's cosine squared. This is the same as this. 1 minus sine times cosine. But instead of this on bottom, I could replace it with cosine squared. Now what can I do? They're not the same yet. They're close, but they're not the same. What else could I do to make them equal to each other on both sides? Lydia?
When you multiply, when you took the cosine off of that side, can you multiply on the top?
Which cosine did I take off?
Like, if you're trying to get the cosine out of the bottom of the right,
Yes.
you multiply it by the top one, like the numerator.
Well, if you did that to one side, you'd have to do it to the other side as well. I see. I kind of think I see what you're doing. Are you saying I should multiply both sides by cosine on top and bottom?
What was that last step? Did you get the cosine on the top?
Oh, the cosine squared here?
Yeah.
I replaced 1 minus sine squared.
Oh.
That's a Pythagorean identity. 1 minus sine squared. Look at this one, Lydia. I got sine squared plus cosine squared equals 1. I subtracted the sine squared over, and so it was just equal to cosine squared. I did a substitution there. Does that make sense?
Yeah, I thought that you were doing the step that I was talking about and you put it on the bottom.
I got you. I know what you're saying too. Yes, sir.
Isn't there any cross out the cosine on top and the
Yeah. This is being divided here. I've got one cosine on top. I've got 2 on bottom. So I can cancel out one of those with one of those. It's like cosine squares means cosine and then another cosine. I'm canceling out one of them. So what am I left with? 1 minus sine over cosine on this side. And guess what? That's the same thing I have on this side. Both sides are equal to each other. Boom. End of the road. I win. Yes, sir.
You want to keep like whatever is on the right side of the equal sign.
So what we want to do, it's a great question. I would say start with the more complicated side. Okay, so I started with the left side. I kept the right side the same. Sometimes we might manipulate both sides, but normally it's best to just manipulate one side. Questions? It is weird. We're spending 4 days doing this. So if after the first day, your brain is out of it a little bit, give it some time. Let it simmer. We'll get better. Let's go to the backside. Now we're simplifying with common denominators. Okay, simplifying with common denominators. I am adding 2 things. This is a fraction I'm trying to add. What do you need in order to add fractions? I don't have that right now. Okay, these are not common denominators. Okay, let's make common denominators. This guy's got cotangent. What does this one need that this one has? Cotangent. So what am I going to have to do to make it be cotangent on bottom? Yeah, I got to multiply by cotangent on top as well. I'm going to multiply the top and bottom by the same thing. Okay, so we get cotangent. Sorry, I made a new problem. We could do that. Let's do this instead. Let's clean up this guy first instead of sine over cotangent. Sorry. What could I do with cotangent? This is sine over cotangent. That's the same thing as sine times what? If I'm dividing by cotangent, it's the same thing as multiplying by tangent. So it'd be the same thing as multiplying by sine over cosine. Let's deal with that. I apologize for switching midstream, but it'll help us out in the end. So cosine of x plus what we're saying. Oh, this is the same thing as sine squared x all over cosine x. So I did 2 things. First of all, I rewrote them in terms of sine and cosine. Do these things have common denominators right now? I can't add them together because they don't have common denominators. What do I need to multiply this guy by? Cosine. This one's got cosine, so this one's going to be multiplied by cosine on top and bottom. So now I'm going to have one denominator. Both denominators are cosine x, so I can put them together. It's cosine x on bottom. What is cosine times cosine going to get me? Cosine squared plus this numerator, which is sine squared. What is cosine squared plus sine squared going to get me? There's my answer. 1 over cosine x. We simplified. We got common denominators and we put them together. you could absolutely make that into a secant squared, or into a secant of x. Yep, that would be another way of doing that as well to finish. In sake of time, let's jump down here. Let's go to letter G. Okay, letter G. We're simplifying by factoring. So that one was common denominators. One more, simplifying by factoring. Okay, these two on the backside are not as common. Conjugates and writing stuff in terms of sine and cosine are more important. But let's simplify by factoring. So I'm telling you, you're going to factor. Sine squared u minus 1. Can I factor this numerator? What if I said x squared minus 1? Could you factor x squared minus 1? What would you factor x squared minus 1 into? X plus 1, x minus 1. That's how you would factor that, correct? Same thing with sine squared u minus 1. Oh, what am I going to factor that into? Sine of u minus 1 and sine of u plus 1. Don't get distracted by it being sine and cosine. You can still factor the same. What about on bottom? What kind of factoring can I do on bottom? Everything's got a cosine in it. So if everything's got a cosine in it, I can factor it out. If I factor out a cosine, what would I be left with? Sine u minus 1. Anything we could do to simplify? This guy would cancel. That guy would cancel. I'm left with sine of u plus 1 all over cosine of u. I'm done. I'm going to leave it like that. There's nothing else more I can do. But I simplified that down. If that sine of u plus 1 was on bottom, we could do some conjugates and work from there. But that's sufficient. Questions on something we did today? It is strange. I know you're looking at me and thinking, man, that was really weird. Yeah, it is. Okay? Again, here are the 4 things we talked about. These 2 are the most important. Rewriting stuff in terms of sine and cosine. Multiplying by conjugates. We're going to use those the most. But don't forget, if you're adding fractions, you need to get common denominators. And don't forget that you could always factor things as well. We will continue to get better. We're going to spend a lot of days getting better at this thing. Okay? Continue to work with me.